2, 1. If we can see both members of a binary pair, and if we can resolve them, and if they're near enough that we can actually distinguish their motion, then we can use astrometry to measure the period and the size of the orbit and learn a lot. We're interested in binary stars. Most binary stars, like most everything, is not going to be near enough for us to measure their motion, and often we won't be able to even resolve the two stars. We'll see the light of the two as one star, just as our eye, unaided, does not distinguish the two members of Albireo. We see one star. Even with a big telescope, the stars are far enough, or one of them is dim enough, we'll only see one star. How do we know by looking at a star that it might actually be a binary? Well, one way is to measure its spectrum. That's what we do. And what will we recognize when we're looking at the spectrum? What about the spectrum will tell us that we're looking at a binary? Well, if we have a binary system that is not oriented such that its orbital motion of the two members is completely tangential, if there's some radial component, then as we saw, that means that some of the time the stars will be moving towards us and sometimes away from us. And furthermore, when one is moving towards us, the other will be moving away. What this will give us is a periodic Doppler shift. We'll see that if you look at the spectrum, there will be some of the lines that will be blue shifted and some others will be red shifted, and then the roles will exchange. So we'll find a periodically shifting Doppler shift. A really caricaturally simple version of this is two stars with one spectral line, and what we see here is two copies of the spectral line moving a greatly exaggerated amount to the right and to the left, to the red and to the blue. And so when one star is moving towards us, the other is moving away from us, we can use the maximal amount of the Doppler shift to estimate the speed with which those two stars are moving. The example below shows the same thing, again caricatured, one spectral line, but here we see that one of the stars is moving faster than the other. One of the lines shifts more than the other line does. That tells us that the two stars are moving, orbiting each other, but one moves more. That means that that star is lighter than the other stars. And in many cases, one of the stars is so dim that we only see one. Then this is very much like discovering a planet through Doppler shifts. You see a star orbiting something, you can try to conclude what it is that that star is orbiting if you know something about the star. Obviously, the more you observe, the more information you can get. So what do we learn by measuring the spectrum? We look at a star, we notice that it has sets of spectral lines that move, are Doppler shifted in opposite directions, and they move back and forth. Well, what can we measure? By measuring how long it takes for the lines to move back and forth, we certainly measure the period with which the two stars that we're actually seeing as one are orbiting each other. We can use the Doppler formula. We measure the maximal shift of some spectral line, and we measure, if it's a double line binary star, we can measure the speeds of each of the individual stars. Now, you may remember that we're only measuring the radial component of the speed, not the tangential component. So I'm going to assume that the system is aligned. If you sort of imagine a set of axes like this, I'm going to put the orbit in the horizontal plane in this picture so that the maximum value of radial velocity towards us or away from us is equal to the actual speed with which the stars are orbiting each other. If the orbit is tilted like this, then this will be false. We'll talk about how we deal with that later. For now, let us assume for simplicity we have circular orbits and no tilt, and we'll have to do some algebra, so bear with me for a bit. So what do? We've measured the two speeds. If I know how fast something is moving, and I know the period, how long it takes to go around a circle, I certainly can figure out the radii of the two circles in which the two stars move. This already tells me something. Remember that the radii of the two circles about which each of the stars move are, in fact, since these are circles about their common center of mass, are related by this equation. So if I measure the two velocities, I already have the ratio of the two masses. I can write that m2 is equal to m1 times v1 over v2. As we predicted from guessing just by looking at the spectrum, the lighter star moves faster than the heavier star. So far, so good. What else can we do? Let's collect some more information. In terms of that, we can write the total mass of the system, because remember, that's what enters into Newton's expression for Kepler's law, m1 plus m2. I write the expression I had for m2. I make a common denominator over here, and I have this relation between m1 and m. So if you tell me m, I can figure out the mass of an individual star. That's what I've done so far. Furthermore, the other parameter that enters into Kepler's formula is the total distance between the two stars. Remember, that's just the sum of the radii of the two circles. Because of the way they orbit, they're always on opposite sides of their respective circles. I plug in the expression that I had for the radii of the two circles, and I find that the total distance between the stars is related to the period and the velocities, or the speeds, that I measure. In this way, remember, period and v's is what we measure. This allows me to compute r. So, now we're going to take all this information that we've accumulated here and plug it into Newton's form of Kepler's law. Remember that P, R, and the total mass are related by this expression. I remind you, on the previous slide, we found this relation between R and the observed quantities, and this relation between M, the observed quantities, and M1. Remember, the mass of one of the stars is what I am after. So what I do first is I plug this expression for R into that expression. I solve this equation for M, multiplying by M dividing by P squared. And then, for this R cubed, I plug the cube of this expression, and then I see some handy-dandy cancellations going on here. Pi's cancel all over the place, and I get left with 1 power of P up top, and I can write an equation that says that M is P over 2 pi G times V1 plus V2 cubed. But I also have this other expression for M in terms of my friend M1, and that's V1 plus V2 M1 over V2. And so I see that 1 power of V1 plus V2 cancels, and multiplying both sides by V2, I finally have an equation for M1 in terms of P, the speeds that I measure, and Newton's constant. I am done. By measuring the Doppler shifts, which gave me the speeds and the period, I can actually measure the mass of a star. Of course, it's easiest to assess this by scaling it relative to, we know that for the Earth and the Sun, I have that the mass of the Sun is equal to the speed of Earth times 1 year times, the speed of the Sun is negligible, let's write the speed of the Earth squared, divided by 2 pi g. And then dividing one expression by the other, I get my happy scaling formula that says, since I know the speed of Earth in its orbit is 29.78 kilometers per second, I can get the mass of each star in units of the solar mass this way, and so we can find masses. Spectroscopic binaries or other binaries stars are a way to measure masses. This is why it's so useful. The two caveats, of course, if the orbits tilt, we're only measuring the radial component of the speed. How would we know if the orbit is tilted? Well, if we're lucky, we would have astrometric measurements, and we can make both, as in the Alpha Centauri version, we can make measurements both in the tangential direction and in the radial direction, and otherwise we have to infer what really we're measuring is one component of the velocity, so the inclination shows up as an overall factor here. And often we only see one of the stars, and then we're only measuring V1. We don't know V2, we can't get complete information, but we can learn a lot of things from this. Binary stars are cool and useful objects.